Can you hear me? Check, check. Okay, so we're good on the sound check for that. And then let's try mic number 2, just because it's fun to have 2 mics. And okay, and are you, this is mic number 2. Mic number 2 only. Mic number 2 is too faint. Mic number 2. Okay. How about now? Okay, I'm going to do a... Okay, just a sec. Check, check, check. Okay, so this is mic number 2. And let me hear what that sounds like on this. Yeah, that's better. Okay, part of it was the adjustment of the mic. I'm going to put it about there. And check, check, check. Okay, so yeah, that I got to give you... Okay, that's about right. Okay. Okay, so this is mic number 2. Checking mic number 2. This is mic number 1. Checking mic number 1. Mic number 1 is high and clipping. Adjusting the gain down on number 1. How does that sound? Okay. Okay, this is mic number 1 only. Mic number 1 only. I might have had mic number 2 on that. Yep. How did it sound to you? That's correct. And so I need to get the camera a little better situated. Okay. Right there. How does that look? Okay. All right. Except for now, I want to move the tripod because I didn't like the tripod position. And that should be back to where it was. Yes, go ahead and laugh at me. Fine, Safan. Okay, so you're good to go? Okay, that's wonderful. So we're live. And welcome to our... All right, and then I guess I can tell the video audience that if they want to see our talk archive, they could go to www.ifa.hawaii.edu and then look under... Oh, wait, why don't you just click on that link right there? Okay. Well, the idea is I'm going to put the link in on the YouTube video. I still have to edit the last video, by the way. So, all right. I will go find Dr. Lundborg, David Lundborg, and see what he is doing. And I'm going to take off the mics because we don't need to be live on the mics. Okay.
I mean, I didn't even know you were here. I just moved from Kihei to Bukalani, so. They do a lot.
A lot of people aren't aware. That's why they do open houses, and that's why they do a monthly talk about astronomy. So if you want to come to the talks, and they're really pretty convenient, just give your email address to them.
Okay.
And they'll just send it to you. You don't have any obligation. It doesn't cost anything. But I'm a volunteer, so I'm not the authority.
There's a lot of experiments going on here.
They work with the summit for the telescopes, and they work with the high performance computer center in Kihei. Because all that data that comes from taking all those pictures
Has to be interpreted.
has to go somewhere, and they actually store it.
Where in Kihei do they? I mean, is it just a storage thing, or do people go there and look at it?
Didn't you know there was a high performance computer center in Kihei? Oh, well, now you know. Actually,
That's beautiful.
yeah,
That works the card.
Okay, thank you. The Safeway is on something, and then I think the next one is Lapoa.
Yeah, I'm gonna go
But
get one.
instead of going downhill, you go uphill.
You go to the left on Bukalani.
Yeah.
There's a technology park, and that's where my eye doctor is, and the Konos restaurant is in there.
Oh,
The
okay.
beer Maui brewing's down there.
Yeah. I haven't been there in years.
And there's a high tech, but yes, I know where it is. It's on the right hand side.
There's a supercomputer in there.
Yeah.
They store all the hand store the stars. I'm not sure what they do exactly in terms of processing. But there's
This is Frank.
pleasure to meet you.
Yeah. So we have two microphones. I'll have you wear this microphone because it is not as good. And then this microphone, we will have the presenter. We are doing a live broadcast to Coronado Shores in Oregon, which is where Safan, she used to work here. She's holding it there, and then we'll also have it on the web.
Okay.
And so what you want to do with this mic is you have it off to the side of your mouth, right about there. And if it feels comfortable, it's in the wrong place. And then I will go find Jeff and see if we can't get him down here. And if you, I would put it literally right about there. Okay.
I think you'll be more aware of the sky. I think they're all good. Oh, yeah, and you don't have to.
Then it says what it talks about.
It always describes the kilometers per second.
A young person to learn. Yeah. Anybody
About
really.
an hour-ish. And some, you almost have to be a physicist. That's not so common. But, you know,
I was thinking, yeah.
yeah, some, it's like you learn terminology you probably never heard before, which I think is
Another language.
interesting because now you're exposed to stuff you wouldn't ordinarily be. But generally, they're learning levels and they're fascinating. I mean, I do it.
You had a big move, though.
Here.
Do you like it so far? Yeah, it's very different.
Okay. So Jeff, your microphone. We're like this.
You're streaming,
David is, yeah, we're streaming. David's going to do an introduction for you, and then Frank, you take over for the next two talks. Is that okay?
And I had a glowing
Oh,
bio
too
for you.
If you
So
want.
you just lost it. That's okay.
That's all right. That's all right. I'll go.
We'll do it double.
So JD, how does this work? Is this really what we have to do?
I don't care, whatever you guys want to do.
I think it's way more.
Yeah. Oh,
I guess it's
Yes.
on. It's on, but it's not
Yes,
on. I can't hear
stop-
anything.
Stop messing with it.
Because you kind of have to, word of mouth is key. Yeah, I'm so sorry to have
On the sound, please.
Testing 1, 2, 3. Hi, I'm talking. Can you hear me?
Yeah, definitely will. Okay. I'm just gonna go upstairs at the end and then,
Yeah, I wanna, I'll go with you.
Okay.
Whenever you're ready.
After.
We can explore afterwards.
Yeah, after.
Is that okay?
Two talks. Yeah, definitely.
So we need to fire this up.
So whenever you are ready, we can go ahead and begin. You want to just leave it alone. And I will sit back there for just a minute and check the sound real quick.
How many hours of that? Yeah, JD.
And then we'll also have the screen as well. And so you're catching these instructions as well, Jeff?
Absolutely.
Okay, great.
I have no idea what you said, but I.
Go into the light. If you can see things, you're not well centered in there.
Okay,
Back
but
against the wall.
but I have to push buttons on my screen, so
I
that's
will
always a
get
problem.
you a PowerPoint presenter. Go ahead and start if you are ready.
I'm going to sit down here.
Good evening, everybody. My name is Dave Blomberg. I'm the Interim Associate Director of the Institute for Astronomy based in Manila. Now the mic is not on to the room, it's just on to the camera, so I will talk louder.
Thank you.
My name is Dave Blomberg. I'm the Interim Associate Director of the Institute for Astronomy. I'd like to welcome you on behalf of our director, Günther Hasinger, who's unfortunately not able to be here tonight, to our 50th anniversary celebration. IfA was founded on July 1st, 1967, 50 years ago. So
Here?
I don't know where the actual establishment ceremony was, but the Institute began from roots here on Maui. The solar work that Jeff will talk about began.
We're going to get to that.
Maui even before the Institute existed.
Sorry, I didn't mean to jump the gun.
But
No,
the
it's
Institute
good.
was founded 50 years ago. We've been celebrating that on 3 islands for the last couple of weeks. As somebody who is new to the Institute, it's been a real opportunity to hear from some of the people who built this great institution and to hear about the work that's been done over this time, building the observatories, scientific discoveries that folks have made, evolution from a band of people taking a lot of risks and doing a lot of brand new work to a well-established world-class research institute. And it's appropriate that we wrap up here tonight on Maui, where the origins of UH astronomy began for the institute, and where we're also celebrating
JD.
the 10th anniversary of this beautiful facility that we're in here. So, we'll have a series of talks about the work that's been done and what we look forward to over the years to come, with Maui continuing to play a central role with the second Pan-STARRS telescope coming online this summer, with DKIS looking at the Daniel K. Inouye Solar Telescope looking forward to first light in 2019, and just a great future and a real legacy that those of us who are here today have inherited from the folks who built this institute and are now tasked to take into the future. And with that, I will hand it over to Jeff Kuhn to talk about the history and about the solar astronomy work in particular that's done here on Maui. Jeff?
Thank you, David. Hey, everybody. Welcome to Maui and the Advanced Technology Research Center and the IfA. The IfA is a broad institution that, as David has just explained, has existed for at least 2 generations. Even though it's been around 2 generations, it's one of the youngest research institutes in the country. And it has amongst its scientific staff telescopes and resources, and has been shepherding the development of telescopes on the best observing sites in the world. How many people have been to Haleakala? That's good. So you recognize this picture. This is from only a couple of weeks ago, taken by Rob Ratkowski, photographer extraordinaire. And it shows what is effectively 50 plus years of development on Haleakala. And what I want to do is I'm going to focus on the solar work, which was the historical beginnings of the Institute for Astronomy, both in Manoa, over in Honolulu, and here in Haleakala. And the name you should remember is this name right here. Walt Steiger died just a few years ago. Walt Steiger's vision started everything out. Did you ever hear of the International Geophysical Year? In 1957, the year I was born, the United States government devoted lots of resources to learning about the environment of the Earth. And that International Geophysical Year was when Walt Steiger, who was teaching physics over in Manoa, realized that the University of Hawaii had access to a small scientific preserve on top of Haleakala that was remarkable. And it was remarkable in the sense that, first off, this was a picture in 1957, and it looks a lot different, doesn't it? It looks incredibly different. This building is still there, and in fact, the amateur astronomers are still using it. All of this stuff is gone, right, Charlie? There's none of that left over. Charlie Fine is in the back. Charlie has been here for many years and knows about it. This was our start, and it started in 1957 with the realization that out in the middle of the Pacific we should be able to track satellites. But the other realization, if you've been up there, do this experiment. Look at the sun, not for too long, and then block it with your thumb. If you do that here, and there aren't any clouds, you're going to see a picture like this picture on the left. So this is your thumb blocking the sun in Pukalani. This is not the sun, right? Your thumb is bigger when you extend it at arm's length than the sun is. What is this? That's scattered light. It's the atmosphere and aerosols, particles, that are creating a really bright sky. If you try to do this on Haleakala, first off, the sky is a lot darker because you can see that my camera can actually see my thumb. Here it just sees the silhouette. And the sky is dark all the way up to the edge of my thumb, except for a couple of things. You see the bright amount of light right here? You know what that's called? It's called diffraction. This is really the halo effect of the atmosphere. This is just an optical effect that happens whenever you have an edge in a light system. It produces scattering, and that scattering is something that we worry about, and in special telescopes we correct, but otherwise it's perfectly dark. That's the magic of Haleakala. And after Walt Steiger realized that, he pushed and he convinced the university there should be a solar program in Hawaii to take advantage of the magic of Haleakala, which back then was only about 19 acres. The second edition of the Journal of Solar Physics had a report from the scientist that was brought in to start that solar program, and his name was John Jeffries. And before John arrived, Walt Steiger got private money to build the first observatory in Hawaii, and it's right here. It's the Meis Solar Observatory. And it was a remarkable place. It was so remarkable that we attracted world-leading scientists from Harvard, from Boulder, from Australia to come and begin a program in solar physics. And in fact, if you wanted to know some of the names, this was John Jeffries, Marie McCabe, Jack Zerker, Frank Orrell, and a bunch of others came in 1965 once Walt had that observatory started. So you build it, and they did come in this case. But it started here, and this was really the beginning of a lot that happened. So this was the satellite tracking. Here was the IGY. There were some experiments to look at the darkness of the sky called zodiacal light, and Meis was started back here in 1964, followed by these eminent scientists. Okay, so that's a great beginning. That's Meis in 1964. And yes, it really was a pink building back then. I don't know why. but it was a pink building. That was the dedication. It was started from Edmund Meis. He was an executive with the Kodak Film Company. And back in those days, film was a big thing. Scientists depended on film. I'm going to show you some spectacular results of their observations that used film. And he put up at the time, it was a few tens of thousands of dollars that got this observatory started. It was private money. This is what a solar observatory looks like. In those days, it was just a very stiff, long pointing platform that you mounted instruments on top of. And this was called the spar, and it was in that dome that I just showed you. Over time, the spar grows like a tree does. Lots of other instruments appeared on it. And this telescope system was used for decades to routinely look at the sun and try and understand how the sun works. This is one of the very early, back in 1971, images that was taken with an instrument on the spar. And I'm going to show you a progression of images that illustrate how we've improved our understanding of the sun in time. Notice these loops. Those loops were a bit of a mystery back in 1971. They're still a bit of a mystery for us. What we know is that the temperature of the gas that makes those loops is about 1 million to 3 million degrees, which is interesting because the temperature of the sun, and you don't see the sun because this is an artificial eclipse created by an instrument on the spar called a coronagraph. We block out the light of the light of the moon, or the light of the sun, and you get to see this outer region. It's about 1 million times fainter. By the way, that's why we went to Haleakala, right? Because you can put your thumb up there and the sky is so dark. So you have the chance of seeing something that's very faint if you build an instrument that doesn't get swamped by that halo that we mentioned that we see down here at these elevations. So that's why we're up on Haleakala. Again, that was the magic. This photograph is proof of that magic. This is a very famous picture that as I was growing up as a graduate student, I saw many times. I didn't realize that it was originally taken in 1979 with that instrument up on the summit. And it shows what's called an eruptive prominence. It's a big storm. We're going to see some other storms. There's some seats over here. Come on around front. It's a big storm. The size of the Earth in this picture is about like that, so it's enormous. And it was an example of how this telescope worked. It ran every day that it was clear, and they took data, and they used it to try to understand what in those days, and what we now call, is space weather. The things that happen on the sun that affect the space between the sun and the Earth. That's what the people look like in 1981. I'm told that there was a lot of sex, drugs, and rock and roll in those days. A lot of mustaches. This guy right here is still around. Stuart Jeffries was, is he here? Oh, there he is. Stand up, Stuart. So Stuart, Don Mickey, can you pick him out? That's him right there. And this is Don. He's hanging on, so the spar, as you can imagine, it tracks the sun and it goes up and down by about 7 feet. And so there's a loft area, and he's hanging on up in the loft looking through the coronagraph at one of those green line images. And it was a pretty active group back then, and I think they had a lot of fun. This is, in comparison, this was the scientists over in Manoa, and they look pretty normal, at kind of a different crowd. This is what an instrument looks like. In fact, this was an instrument that Don Mickey built to help understand why those loops existed and why they exploded and why they sent gas out into space. Don and his collaborators in the mid-'80s began the development of what was called the imaging vector magnetograph. And so we're going to get back to that in a minute, but to understand what makes things happen and to be able to predict when those things will affect life here on Earth, we needed instruments like this. And for about almost a decade, this was the only instrument that could actually look on the surface of the sun and see the magnetism in a way that told us what it would do next. You know who that guy is? This is basically the end of the days of the SPAR. So as space observations became more possible, and as we had more resources going to other places in solar studies, the SPAR saw its end in the mid-2000s. And I'm not sure what JD was doing here, but this was the last days of the imaging vector magnetograph. Instruments were changing a lot, and that's what we're part of now. I'll show you. So the problem in understanding the sun is that, did you see that little burp there? So this is a space observation. And now that we have satellites, we could look at the sun continuously. That space event corresponds in a different picture. In a still frame, it looks like this. So remember those loops that Mary McCabe and Don Mickey showed in those film images. These are the same loops now taken from space. And we can see in much greater detail when we get above the atmosphere and we look. This is almost an X-ray wavelengths. And you can see from the last picture that they create blurps of energy that we call coronal mass ejections and flares that eject particles and X-rays into outer space that can be bad news for us. So our job, and the reason why we're here and up on Haleakala, is to understand what makes that happen, and ultimately to be able to predict it. So you look at this image and you might say, why should there be a loop in the atmosphere of the sun? Any thoughts about what could cause that? There's the cause. It looks like what you've seen if you've seen a magnet with filings on it. So we've always thought that the cause of all of this activity is the magnetism on the sun, but we've never been able to measure that magnetism. We see the pictures, but we can't really understand it if we can measure it, because the strength of that magnetism is about the same strength as the magnetic field on the Earth. And so it's pretty weak. And how do we measure it out there in space and on the sun? That's our problem. In the early phase of the development of the Meis Observatory, we could take pictures, just like this picture from space, but we couldn't do the hard science of understanding how magnetism makes things happen. Why should you care? Well, here's a reason. That blurb that I showed you in that short movie corresponds to a time. So here's a map of the United States. And what you see on this scale is the uncertainty in the landing of a plane by GPS systems. So this is the landing error in feet. And you might imagine that if you don't know to within a few feet where the plane is, if you don't have visual landing, you will care about that. And so during that flare, except in the center part of the United States, towards the edges, California, for example, GPS wasn't usable. Now, there are other problems with that energy that comes from the sun. It interrupts the radio communication, especially at northern latitudes, to planes. And in very large events, it can destroy satellites. And in the early days, it also knocked out power grids. So there's a real cost. And in some cases, that cost is in billions of dollars, much more than the cost of the one telescope I'm going to show you here in a minute. So there was another phase in the IfA that started towards the end of 1993. The only people that existed beyond the early phase to the phase we're in right now are Don Mickey and Barry Labonte. Barry Labonte moved, has since died, and Don has retired into comfort in Oregon. The scientists who are here now are indicated as such. JD is here. These are scientists that are building the instrument I'm going to show you in a minute. Those that exist now Stuart is actually taken a position in Georgia State, but we hope he stays here. And Shadia is over in Manoa. So there are a few of us. There are about 4 of us, 4.5 with Stuart's here. This phase corresponds to the development of a fair amount of activity. The red flag events were the selection of what was called the Advanced Technology Solar Telescope. You see it up on the mountain. I showed it to you on Rob's picture. It's a big deal, and we'll say a little bit more about that. Some other telescopes, so the Air Force has its facility. The laser ranging has morphed in various ways, but it's still going on. This is the building you're in, the Advanced Technology Research Center. That appeared about 10 years ago, and we're celebrating its 10th anniversary this year also. The DKIS construction started here. That's that big solar telescope. Its first light and operations are due in 2020, based on the current schedule. So there actually is a lot going on. The IfA during this phase put most of its energy into Mauna Kea. And we're trying to convince the IfA that, hey, there's a lot going on in Maui. Remember your history, how you got started. Here's one of the telescopes that started in soon after I came here. This was a telescope designed to show that it's possible to measure the magnetism, to be quantitative, and to try and build physical theories that help us know how the sun does what it does. And it succeeded. It made a magnetic map of those loops. And so after many days of development and many hours of observations, Hao Shen-Lin and others were able to show that we could measure magnetism. And the strength of the magnetism was about what it was on the Earth. And it corresponded to these real loops of magnetic field that we could model, but only measure with Haleakala. Solar Sea is still there. Gabe, you'll see, is making liquid nitrogen ice cream outside. And he is finishing another project to show how magnetism in the sun's atmosphere can be measured. So compare this image that we get from space, these fine loops. We really have to do better than this very crude. This is a very crude contour map, right? Compared to what we know is actually going on in the sun. And while we can measure the magnetism, we can't really predict what happens or distinguish models in that magnetic picture. So the other thing that we recognize is if you had 4 micron eyes, and in fact upstairs take a look at the infrared camera that the Air Force group is demonstrating. If you take that outside and you hold your thumb up on Haleakala, you not only get to see the sky, but you can directly see the corona. So Haleakala is even more magic in studying the outer part of the sun when we build instruments that can see beyond the wavelengths that our eye can see. So starting in around 2001, we tried to convince the international community that the best place in the world for a solar observatory is right up there. And we started with satellite measurements of 100 to 150 different sites, and then the National Solar Observatory put towers in 6 different sites, and for a couple of years made very detailed measurements. And the 3 best sites from those measurements were Big Bear, so there's a lake at a high altitude to the east of Los Angeles called Big Bear Observatory. That was one of the best sites. And then in Tenerife, an island off Africa, is another observatory, which was also a very good site. And then here's Haleakala. Okay, so there are a bunch of numbers on here. I just wanted you to see why we ended up here. Here's the sky brightness measured in millionths of the brightness of the disk of the sun. And from Big Bear, the median values range from 96 to 800. From Tenerife, they range from 31 to 114. And Haleakala, the median was 5.8. So it's not just what you think of when you stick your thumb up and look. It really is a dark sky, and darker than any place else than we can measure. There's a reason for that. Part of it is that the dust in the air is so we can. There are special rooms that have very low amounts of dust, and we have in the lab, maybe you'll see it, we have a dust counter. If you put a dust counter up on the summit, the number of dust particles, instead of 721,000, is 27,000 compared to 654,000. So it's a very clean environment, and there's a good reason why that site is so dark. It has to do with the aerosols. Not only that, if you want to know how good a site is going to be for the twinkling of the atmosphere, you can measure what we call, astronomers call, the scene. And we, on each one of these towers, at each one of the best of the 6 observatories, we had a tower for years, and we could measure how good the scene was. In other words, how much is the atmosphere going to blur what we see? And the higher this number, the smaller the blurring, and this red line is Haleakala. And Haleakala at all elevations above the ground, except below about 13 meters, is the best place in the world for seeing. Big Bear Solar Observatory for low heights above the ground is better, but this is why the telescope is up at some height, so we can also get very clear, pristine views. So we convinced the National Solar Observatory that the best place in the world to build this telescope is Haleakala. Then we convinced the state that we needed a laboratory where we could build instruments for that telescope. And we did, and you're in it. This is the observatory, and these are some of the laboratories, and we hope today you'll take a look and see how things are going. This is what DKIS looks like, at least on the computer screen. It's a telescope that looks a lot like that Solar Sea telescope in that it doesn't have anything in front of the primary mirror. This is called an off-axis telescope. The light comes down into what's called a coude room, where all the instruments are. So it's a big carousel where the instruments live, and then a region up here. And notice this structure. I'm going to show you that structure is just now being put together. That's what supports the mirror and guides the light. Here's what it looked like. We were up there last week. Here's some riffraff. Here's that structure that holds the mirror. And I don't know, you can maybe get a better idea of how big it is if I start a little movie segment. So it's real. Within the next couple of months, the mirror will come up, and we will have the workings of a real telescope. Lots and lots of details to work out. It won't be for another almost 2 years in 2018, 2020, that everything is right. I guess that's more than 2 years, isn't it? 2.5. The mirror will go up in a couple of months. Mike, you may know exactly when. In a few weeks, perhaps. The question was, when might the mirror go up, and the mirror may go up in a few weeks. This is what you remember seeing the IVM. This is Don Mickey now. Don Mickey is one of our collaborators in building this modern instrument that replaces the IVM. This is a group up in the earlier days when the telescope wasn't done. This is our primary builder for the instrument. He's called the instrument scientist, and this is what an instrument today looks like. It's in a clean tent, and if you go into the lab tour, you'll see what it looks like. This is about a $6 million instrument, going on a $345 million telescope, which happens to be, in today dollars, the most expensive optical telescope on the ground that humans have built. The Keck telescopes, when they were built, were about 80 million. Subaru telescope was about 120 million. So this is the instrument exposed, and that's the main team. Here's some data that's taken with it. These are now infrared raw images that were taken a week ago. And finally, this is what we think things will look like in the winter of 2020 when it turns on for the. Can I get it back? There it is. Back into the future. That's one of your photoshopped images, I think, Charlie. So that was actually. It looks like the telescope is there already. In fact, it does look a lot like that, but that was photoshopped onto the summit. And that is snow. We do get snow up there. So with that, I'm finished, and thank you for listening, and come back in a few years to learn more.
Sir, can I ask you a
Absolutely.
Is there any concern at all about light pollution?
So, from civilization. So the question is there any concern about light pollution? So we don't have such a problem because we observe during the day, but there is real concern at night about light pollution. So we're with the biologists that don't want to see lots of up-looking lights that disturb the turtles and some of the pelagic birds. It also disturbs the astronomers. So we're hoping very much that we can become more friendly with our up-looking lights and we can create an environment that's friendly for nighttime astronomy. But for daytime, it's not so bad. Yes? Yes, so the question was how many telescopes are up on the summit? There are several. This is, okay, I can point them out. So this is the Air Force facility. This is also part of the Air Force facility. There's an educational telescope, which is here, just used for educating students all over the world that JD's very, very much. That's the Fox telescope, or the Las Cumbres Observatory Telescope Network. There's some small telescopes over here. This is the Meis observatory that we originally saw, and you can see that it's now pretty much dwarfed by the DKIS, which is right next to it. So I think I'm running over. I want to thank everybody for coming. I'll be around and I can help answer questions.
The next presentation should be in about 10 minutes. It's going to be from Dr. Shad, and he's going to talk about a subject that is pretty much unknown to me, but it's called after Tom Shad. Yeah, I'm not sure if the agenda changed since. But the Citizen Cave experiment, worth visiting and seeing what Tom Shad, or perhaps the person who's identified there did it. Thanks for joining us.
Jeff?
Yes.
The slide you showed at the end with the, he's building, he said in the tent, he's building that and we look at it? Yes. I don't see that listed here.
So it's in the lab tour.
Okay,
So when you take the lab tour, they will point out
take the lab tour, okay. Okay.
I got 4 emails today about the agenda, but I still wasn't covered. They're all good. We're looking for the that's why it's been closed. Because the door stopped. You're Mark.
Yeah, that's right.
So you're clearly the next speaker. Good. I'm Frank. Good. We'll introduce you.
Okay, well, so we got 5 minutes or something.
Yeah.
Start. Get this So, that's good.
I do too, yeah. Yeah. Nobody came back with the microphone.
This year?
Oh, you got one. Okay.
I don't know.
So you're good.
Check 1, 2.
Back there to know that's actually working. So Jeff left. That's good.
Yeah, yeah, it's here. You know, somebody knows how to turn it on and stuff.
And you knew at those neighbors. Got two sheets over there.
Hey, Tony, what you doing, man? Back up there.
Yeah.
Yes,
Don, you can sit there.
Here, do you want to sit? Okay. Sit in front. I can sit.
That's right.
Crutch.
So we're doing action here.
Yeah. I saw Trappist.
Yeah.
Okay, where's the mic we do have?
I'm thinking it's behind here. Oh, no, I'm thinking.
That's the mic we, yeah, that is the mic we do have. That's okay. That's the mic we really, that's one we want to watch, yeah.
All right.
The other one, it'll turn up. I doubt anyone's
The
going to walk off.
presentation introduction was nothing that special.
Yeah.
Okay. Just,
Yeah, and then I'll go look for Mark.
yeah.
Robert, hey, long time no see.
Just planets, there are no. I mean, Mars is the only one that's even possible.
Yes, Mark Wellman. He, yeah. Yeah, all three speakers are Dr. Longboard. I think it's also Dr. but it was the insurance doctor.
You've been introduced.
Generated?
Yeah.
What's going on?
Okay, so he
that's the Thursday.
Yes, I know.
Didn't start.
Yeah.
Yeah, I just did.
Oh, there it is.
But just look at it and see. Okay.
What they're gonna do.
Is there anyone who hasn't gotten the agenda? They're at the front desk. You can have one. You can have two, actually. Anyone else? Well, I guess the three that have others are at the front desk. And should be happy to-
The other L. Cast is amazing.
Yeah. Center.
Possibly.
I think
I've got a broken heel after about a week and a half of this month.
Right there. Right at the corner of your mouth. So it's not annoying, you're not doing it right. And try to stand in the light. Right to the wall, that way people can see you. We are kind of, if they're still paying attention at the moment, we're going to shout out to our friends who are on the shore. We'll have other video drops. Okay. All right.
You know,
okay? I'm okay. Gotta go by and check out the generator I installed. 20 kW right there. 30 kW generator we installed in highly mighty storage. Nothing wrong with it. You don't have to, so I want you to go by and look at it. So I'll hobble over there and look at it for you.
I'm going to write that down in my book right now.
He's a pretty interesting character.
Check this mic out.
Can you hear me, JD? Why don't you give a shout out to our friends at Coronado Shores? Aloha, Coronado Shores. We're about to start. Are you okay to...
Let me ask JD if this is coming through here. You hear that, JD? You hear anything?
Beautiful.
Yeah.
Go ahead and put it on your mark. Be right up. There he is.
This goes on the right side, I guess.
Yeah, so Safan is over in Coronado Shores, and she has all of her neighbors come together in the community center, and so every now and then we try to give them a shout out or two.
I heard you speaking to Savannah and thinking, the poor guy can't leave IfA, can he?
She is Safan is a permanent part of the IfA. We love her in perpetuity.
It's falling off.
There we go.
Okay.
Yeah, there you go.
Check
All
one,
right.
two.
Let me go back.
Did you give a talk already? No.
Just the intro.
You're the MC, okay.
Yes.
Yeah, check 1, 2, test. Testing 1, 2. Can you hear me, JD? Is that coming through? Is that coming through? Yeah, okay.
Good to go?
I think so. Let's put this in my... Let's see now, changing channels here.
No, nothing.
Yeah. I just click it there, okay. Okay.
Good, Mark.
Yep, fire away.
Aloha, everyone. Welcome to the Institute for Astronomy and the annual... Mic is not... the mic is not for the folks in the audience. The mic is for the folks that are being... I need to speak louder. Thank you. The mic is not for the folks here locally. It's really for the people that are getting the streaming video. So if you're having a problem hearing, please speak up. And thank you. We're here tonight to introduce Dr. Mark Willman. Dr. Mark Willman is really a very special guest for Institute for Astronomy. His subject is habitable worlds. How far are we willing to go? Mark is interested in habitable planets as an aspect of the ancient question of how widespread life is in the universe. I believe habitable is the key word here. Just think habitable. He is particularly fond of the one we're standing on, as I hope we all are, and would like to see its habitable status preserved. He'll discuss a remarkable recent discovery of 7 possible Earths strung out like pearls around TRAPPIST-1 and how that relates to our home, sweet home. Are you curious to see if we are alone? I hope that's the case. Please welcome and give your full attention to Mark. Please, Mark.
Thank you, Frank. Hello, everybody. Welcome, and it's a nice occasion to celebrate the anniversary of the IfA here. Now, I gave tonight I'm going to talk about this particular discovery. It was just made in the last 2 years, and this is remarkable. I gave a talk on this a couple of months ago, so some of you may have been here, may have seen that. I'm going to summarize some of those results, so you may see some of the same information. But then that segues into our planet, as Frank was saying, and what we need to do to preserve life here, which is another issue. So let's start off with TRAPPIST-1. Now this was a discovery 2 years ago, actually. They found this red dwarf. It's 40 light years away. That's close in galactic terms. And it was believed for a long time, for the last 20 years, since we've been discovering planets. We've now found thousands of planets around other stars, so they're very common, it turns out. We are not unique as far as being a planet. But it was believed that planets around red dwarfs, which are the most common kind of star in the universe, probably 2/3, maybe even 3/4 of all stars are red dwarfs. We don't really know exactly. The reason there's such uncertainty is because they're hard to detect. They're very small and therefore faint. And so we may have missed some of them in our own neighborhood. But this was found, TRAPPIST-1 is named after a telescope in Chile. And it's actually named after a beer. This is a Belgian beer you can find in the liquor store. I have not tried it. I hear it's a good beer. The Trappists were monks, as you know, and they've been around for centuries. And they were given a royal privilege of selling this beer, not for profit. They're only allowed to support their monastery and do charitable works with the income. So, but anyway, there's two of these telescopes, 1 and 2, and it was believed that red dwarfs might be inhospitable to life because they're so small. It wasn't certain that they would have planets even. And if they did have planets, the simulations you do on a computer suggested that the planets would be tidally locked. In other words, when they go around the star, the same face would be towards the star all the time, like our moon is to our planet. So there's a slight mass distribution that locks the orbiting to the parent body. And so that was believed to be a showstopper for life because it would be baking hot on the close side and freezing cold on the far side, not very hospitable. Well, about 10 years ago, Jill Tarter questioned that conventional wisdom. She said, you know, if there's an atmosphere and an ocean, say, on this planet, then that would help redistribute the heat from the hot side to the cold side. And so it would moderate these extreme conditions. So maybe we should revisit this question. Maybe we should consider red dwarfs. So this project started up. The principal investigator is a Belgian. That's why he named it after a Belgian beer. And they built these small telescopes. They're only about 30 inches, only about this big, very small. When you consider the big professional telescopes, you know, up to 10 meters nowadays, you know, they're discussing a possible 30 meter on Mauna Kea. There's a lot of controversy about that, but the trend in history of telescopes is just to get bigger and bigger. You need more photons to see things. However, they used a tricky technique. What they're doing is just staring at a given spot in the sky, and they watch the light very closely. They measure the light, and you see it's going along steadily, and then once in a while, around one of the stars, there will be a dip in the light, and you'll see it drop down, and then if you wait long enough, you may see that dip come around. And if it's periodic, if you see that dip come regularly, you know, every month or every week or every year or whatever, then that tells you that there's an orbiting body that's blocking the light, casting a shadow on your telescope. And that's what the dip in the light is. I'll show you a picture here. Let me just mention Bruno while we're at it here. Giordano Bruno, now there's an ancient argument that goes back thousands of years to the ancient Greeks over whether there is life elsewhere in the universe, in particular habitable planets. And Plato and Aristotle were very smart guys. They said Earth is unique. Giordano, this was, time in the Greeks, 2,000 years ago. The ancient Greeks. Giordano Bruno now, there's a picture of him, nice looking guy. And he said there are countless suns, countless Earths, all rotating around their suns in the same way as the 7 planets of our system, the 7 planets they knew in 1580 or so when he said this. Now, this was considered heresy because if there are other planets around other stars, then presumably they have other gods. And the Catholic Church did not like that idea. So they burned poor Bruno at the stake. So he came to a bad end, but it turned out he was right. Plato and Aristotle were wrong. Now these are the light curves I was talking about. So here we are, here's time. So this is in minutes. So here's 0 to 60, that's an hour. So you're seeing a 2-hour period here as you go across. And then up the side here we have the brightness that we're measuring from this star. So here's 100%, 98%, 96%, and so on. Now this 100% applies to this particular curve. These other curves are just offset for clarity. So you see the lights going along. There's some noise there. You know, you never get precise measurements. There's turbulence in the atmosphere and so on. So your light is bouncing around, and then you see something dramatic happen. All of a sudden it gets darker. It gets about 1% darker. Here's 100%, 98%. So there you're about 99%. So you drop about 1% in the brightness. Then it stays there for a while. Then it goes back up to where it was and continues on. Now, if you watch this on a longer graph, you will see this same curve repeating at regular intervals. And this is these curves are all from the same star, from this TRAPPIST-1 red dwarf star that's 40 light years away. And so you count 1, 2, 3, 4, 5, 6, 7 planets here that are orbiting this star. Now this is a very small star. The planets, let me excuse me, let me show you a picture. These are artists' renditions of the planets. So this is imagination. I don't approve of this sort of thing. If you're going to present facts, scientific facts, you shouldn't mix it up with Hollywood. But this NASA feels like this. It just to put gray blobs here wouldn't be the same. So they like to. So ignore the colors and so on. We have no idea what they look like. We just know they're there. But we do know the sizes. These are the orbital periods: 1.5 days, 2 days, and so on, up to 12 days. The farthest one out from the star is 20 days. So they're very fast orbits around the star. And then you've got the distance to the star. Now this is in the AU. Earth is 1 AU from the sun, so we use that as a standard to compare. So now here you're at 0.01, so you're 1%. You're inside the orbit of our Mercury, which is about 40% of an AU. So even the outermost star here is at 0.06 AU. So these are all very close. It's like a miniature solar system. And then we have very precise measurements for the radius, and these are given in Earth radii. So that's 9% bigger than Earth, 6%, 0.77. You see, they're all very close to Earth size. Now this is just totally unexpected. It was a shock. Nobody imagined that you would find 7 planets around the same star, all Earth size, 7 Earths in a row. It's unbelievable. It gets even better. We can also determine the mass precisely. 0.85% of Earth and so on. They're all 1.38, 0.4. Okay, that one's about half the mass of Earth, but the rest are pretty close to Earth size, mass. Yeah.
And their star is how big in proportion to our?
Oh, their star, this TRAPPIST, yeah.
Repeat the question, please.
Okay, for online people, the question is, how big is TRAPPIST-1, this red dwarf, compared to our sun? And it's much smaller. It's about 10% of the diameter. So it's a very small star, these red dwarfs. That's why they're hard to find. And so the planets, so there's no Jupiters, there's no gas giants, ice giants. There's nothing like that equivalent in this system. There wasn't that much mass to collect into the planets. But there was enough to make Earths, and it made 7 Earths in a row. Unbelievable, huh? So, okay, for comparison, here's our solar system: Mercury, Venus, Earth, Mars. And you notice, well, Venus is very close to Earth size also, but these are all about Earth size. That's amazing. Now, what we're interested in here is are these planets habitable? And so there's several I just listed these factors as criteria of habitability. You got to have the right temperatures. Mainly you want water oceans, right? We think that's important for life, to have water. So the temperature and the water kind of go together. Gravity, if it's, you know, if the gravity is 2 or 3 times Earth's gravity, then we won't be able to live there. You couldn't walk around, so we're too weak. It could be smaller gravity than we have. That'd be okay, but you'd like the same gravity as we have. We've evolved to live on this planet, so our muscles, our skeletons, everything is designed around that. The atmosphere has to be suitable. You got to worry about radiation. That was a big fear on these red dwarfs because when they're first formed, they put out a lot of radiation, which would sterilize the surface of the planet. Okay, so I'll just quickly run through these. Temperature and water, like we said, are really connected. It's the same factor. And the outermost planet, number 7 in that list, is at the edge of the habitable zone. They just do a calculation. They know the temperature of the star, so if you know the distance from the star, you can figure out how hot the planet would be. So number 7, all the way out, is right at the outer edge of the habitability. Then you work your way in. The inner 2, the closest 2 are tidally locked. They're pretty sure about that. Like our planet Mercury is to the sun. Well, no, it's not tidally locked, but it is in a spin-orbit resonance. So it spins 3 times when it makes 2 orbits around the sun, and then it repeats that pattern over and over again. So these may be tidally locked, or they might be in spin-orbit resonances. Obviously, you'd prefer spin-orbit resonances. That means the planet is rotating, and it would have a day-night cycle. Otherwise, you got permanent daylight, permanent darkness. Not so nice. And okay, but now this is what Jill Tarter pointed out. She said in this paper, a famous paper 10 years ago, she said, well, so what? So what if they're tidally locked? That means you've got a hot side and a cold side, but in between there has to be a Goldilocks region, right? Somewhere in between hot and cold, it's got to be like Maui. And so there could be an ocean. And in fact, it's a weird concept, but this ocean would be along the terminator. The terminator is between the light and the dark side. That's the terminator. So you could have a terminator ocean, a ring around the planet. And like I said, the atmosphere could also help distribute the heat, and an ocean would do the same thing. Now the gravity, I'm going through this real fast. If you want to see more detail on this, I gave a long talk, an hour and a quarter, about 2 months ago, and that's online. Just look up Mark Willman, TRAPPIST-1, and Google that, or DuckDuckGo if you don't like to be tracked, and you'll find the talk, and you can check out more details. But just you remember F equals ma from high school physics, right? Force equals mass times acceleration. That's Newton came up with that. Aristotle said force equals mass times velocity. That was wrong. Aristotle did make mistakes. And then Newton also came up with this. The particular force of gravity is this mass of the parent body times the mass of the object that's being attracted divided by the distance squared, the radius out to the... So that gives you so if you plug this force in here, then you see m will cancel on both sides, and you end up with the acceleration is just, this is just a constant, that doesn't matter. This is the mass of the object and the distance out squared. Now you saw in that last picture, the last graph, we had the mass precisely of these planets and the radius. So we know both of these numbers. So we can calculate the exact gravity, and here they are. And you'll see they're all close to 1. They're very close to Earth's gravity, except this one, 1.23. That's about a quarter heavier. So if you're a 160-pound person on planet number 2, you would weigh 200 pounds. You could still walk, but it would be an effort. It'd be like carrying a 40-pound pack on your back all the time. You wouldn't want to walk for 10 miles, maybe. But you see, the others are very close, or lighter. Well, lighter's no problem. Then you're Superman, you know. That's cool. And then the atmosphere, just a warning here. Think Venus. Bad news. 90 times the pressure of Earth's atmosphere. It's got sulfur dioxide, hydrogen sulfide, And it's not pleasant for human beings are never going to go to Venus. You could send a robot. Even robots are tricky. It's so hot. It's what is it? 900 degrees Fahrenheit. Even a robot. The Russians have dropped in. The U.S. has dropped in some probes there. They last 20 minutes. You know, fried. So that's a tough one. Radiation shielding. JD, you're going to give me a 3-4 minute warning. I got a lot of material here. I'm trying to squeeze into 20 minutes. Now, we have a magnetic field on Earth that protects us from our solar radiation that comes in. So that's the Aurora Borealis in Alaska and so on. So the charged particles come in, they bend through that magnetic field, curves in, and they tend to come in at the poles, put on a fantastic display. That's nice, but on these red dwarfs, it can be very intense radiation. The first few 100 million years. After that, it calms down, and then red dwarfs live virtually forever because they're so cool. Their fuel lasts a long, long time. What do they say? It's like hundreds of billions of years compared to our star, which has a lifespan of 10 billion years. We're about halfway through. We're at 5 billion now. So, and in fact, in 1 billion years, the sun is slowly heating up. It's going to fry our oceans off. And so we'll be toast. We'll be gone, of course, long before that. But the average species on Earth lives 2 to 3 million years. Now, we're a very young species. We're only a couple 100,000 years old. So, but because of our technologies and so on, we're going to alter ourselves very quickly here. And we won't be recognizable in 1,000 years, probably. So 1 million years, that's a ridiculously long time span. You can't talk about humanity in 1 million years. There won't be any such thing. And then an ozone layer. You need an ozone layer to protect you from UV radiation. And remember, we had a hole in the Antarctic a couple decades ago, and then the nations of the planet all decided we've got to stop this. So they phased out CFCs, which were made by DuPont, I think. Anyway, that hole is now closing up. So we took wise action. That's a good example of if people cooperate if we cooperate as a species, we can solve these problems. Trouble is, we haven't really matured politically, and so we tend to fight over resources. But the other option is hide behind the Terminator. If you're here's the sun, here's your planet, just stay back on this side, and you'll be protected from radiation. Okay, life. Well, let's move on. That's just guesswork. We don't know. So the summary temperature is good. It's possible that with those factors we've mentioned, all 7 of these planets are habitable. They may all 7 have oceans. Life could have evolved if life tends to evolve everywhere. We don't know yet. We only have one example. But it could have evolved 7 times independently. You could have 7 independent DNAs on these different planets. Now, we could go into questions about that. What happens when you exchange rocks and so on between them with bacteria? They'd be very easy to do there. They're so close together. We get some rocks from Mars. We get a lot. We get some from the moon. Most of our meteorites come from asteroids that are very close to Earth. But we do have some from the moon. We have I don't know, what do we have? 60,000 meteorites in our collections, I think, and we've got a few hundred from Mars, something like that. So it's hard to get here from Mars. You got to, anyway. So temperature, water, gravity, they could all be there. They could be nice. Atmosphere, we don't know. Radiation shielding, well, there are ways to get around that. Life, we can't rule it out. There could be life. Now, this was the conclusion of my talk a couple months ago. The moral is that there might be nice places there to live, but we don't know for sure yet until we get a lot more information. However, Earth is perfect. That's kind of the take-home message here. We evolved here. We fit on this planet perfectly. And the other problem is, even if these are beautiful, fantastic places, just like Maui, with islands in the ocean, surfers at the beach, and so on, You can't get there. It's 40 light years away. We'll never be able to get there, regardless of what Hollywood says in sci-fi movies. The speed of light, as far as we know, that's a fundamental limit. And we can't even go anywhere close to the speed of light. We'll never be able to go more than 10% of the speed of the light because of the sand grain nuclear bomb problem. When you're going that fast, a sand grain has so much kinetic energy that if you're plowing through space, that sand grain hits your spaceship, it's like a nuclear bomb. There's no way around that that we know of. So even if we had technology that could propel us to those speeds, we couldn't get a human being there. We might be able to get a little chip or something there. If we sent enough of them, maybe a few would get through. Maybe we could take a picture or something. But that's it. Even 1,000 years from now, we won't be able to put a human being on another star. So no matter how nice it is, we're like, you know, Moses looking across the River Jordan. We'll never go to the Promised Land. Now that brings me to the final part of this, which is, how well are we taking care of this planet? We should take better care. This part I like. We should take better care of the planet we share. Oh, I'm not done. 3 more slides. Now, y'all heard about climate change. This is a very controversial topic. I'm kind of sticking my neck out here. Scientists don't like to get involved in political questions because it's dangerous. I don't care. I'm old. What are they going to do to me? I'll tell you the truth. I'll tell you the truth as far as I see it. Now, I'm going to let you be the scientist here. I'm just going to present you some facts, and you draw your own conclusions. I'm not going to, I do have an opinion, but I'm going to try and restrain myself. And look at this 140-year temperature graph. Here's 2020. Here we are right here. We're about 17. We're right here now. That's last year, 2016. This is 1880. We have actual, the British Navy and so on took measurements of the oceans and air temperatures very accurately. So we have very accurate actual thermometer measurements for this time period, for 140 years. Before that, we have to use other methods, tree rings, ice cores, ice bubbles, and things like that. But these are very accurate measurements. Now, what do you see? Well, we're going along 1880, bum, bum, bum. Things, year to year, it changes. Here it surges up a little, and it's back down, no big deal. Now, what happens here? 1960. Whoo! I shouldn't say who. That's putting a judgment value on this. So anyway, something starts to happen in 1960, dramatic. Now, do you think the temperature is increasing? I'll leave that to your judgment. But look at the typical variation from year to year. It bounces around, then boom, 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 boom. Now look at the last 3 years. This is 4 years ago. 1, 2, 3. Now this is degrees centigrade, Celsius. That's almost 2 degrees Fahrenheit each one. So that's 0.6, 0.7, 0.8. Each one of these lines is 1/10 of a degree higher. Now here we're bouncing around over from 1880 to 1960. For 80 years, we changed from an average of about minus 0.2 up to 0. So we heated up about 2/10 of a degree in almost a century. Now, in the last 4 years, we've heated up, the last 3 years, we've heated up 1, 2, 3/10 of a degree. We are now up 1.1 Celsius from the long-term record, which is 2 degrees Fahrenheit. The planet is now 2 degrees hotter. And 0.3 of that, which would be 0.6 degrees Fahrenheit, is in the last 3 years. So stay tuned for 2017. Every year, out of the 15 of the 16 hottest years on record ever are since 2000. And in the last 4 years, last 3 years, every year is a huge jump, 1/10 of a degree. It doesn't sound like much, but that's in 1 year. Okay, that's a short term. That's in the last century and a half.
How do they measure that?
These are measured with thermometers. This is actual, they dropped the British Navy all over the world. This is an average, the whole globe. They actually drop thermometers into the ocean. They put them in the air. We've got accurate temperatures, very accurate for this period.
Surface water or?
It's, I don't know. Now I'm going to I'd like to follow up with a talk in a couple of months. Time's up. Okay, last slide. Last 2 slides here. Now let's look at 2,000 years. Same idea again. Here's 2,000 years. Here's the temperature. Here we are, 2,000 years. This goes back to the ancient Greeks, banging around, banging around. These are all different ways of measuring it. So this is a consensus. Something is happening right here, very dramatic. Let's take one last slide. Now let's go back 500,000 years. These are various measurements. These are the ice ages. These are 100, so this is 450,000 years ago, 350. Each ice age comes every 100,000 years. That has to do with the orbit of the Earth. It wobbles around. So when it tips, the pole tips a little closer to the sun, we heat up. When you're more vertical, then you cool off. So we have a regular cycle on the Earth. Every 100,000 years, we go through an ice age. Most of that time, we're about 8 degrees cooler than now, 8 degrees centigrade. That's a lot. So there's a big change there. Then you bump up when you tilt closer to the sun. And you jump up always the same amount. You jump up 8 degrees every time. It's very regular, very predictable. These are called interglacials. We are now in an interglacial. That's why we have civilization, because we can now grow crops worldwide. We can support cities. This has been going on for about 11,000 years. That's when agriculture started. Humans started agriculture. Before that, we were hunter-gatherers. So that's only because of this fortunate circumstance. If we were in the Ice Age, it'd be back to hunting, only there's nothing left to hunt. So we're now fully committed. We've wiped out all the big game. We can't support almost 8 billion people now. 7.5 billion people cannot live off deer. There aren't any more deer. There's a few deer, but we have to have modern agriculture to survive as a species now. We're committed technologically. So if something goes wrong here, then it's very bad news. So I'm making a judgment call there. Okay, I'll let you think about that. But you see, here we are. These only last about 15,000 years, usually 15 to 20,000 years for an interglacial warm period. And we're well through our phase here. But now, okay, last comment. Time's up. You hear this thing. They say that the international agreements, they want to limit the rise to 2 degrees. Well, I kept thinking, why'd they pick 2 degrees? Turns out that's about the noise in this. You can see is about 2 degrees. These are degrees Celsius. So that's 2 degrees. This is 2 degrees. If we go hotter than this, 2 degrees, then we're heading into uncharted territory. The planet hasn't been that hot in at least 500,000 years. Actually, it's worse than that, but this will show you that. Thank you very much. I think I probably burned up all my time and then some, so we probably don't have time for questions. Is that right, JD?
It'll take me a moment to set up my computer.
Okay, here, you want to plug into this? Here, go ahead. Okay, if somebody has a quick question, I could talk while we're switching off here.
You gave that chart. You said in the 1940s the amount of. I saw that the temperature went up
Here you go.
quickly in the 1940s. Is there anything to account for that?
No, I haven't. I noticed that there is a steep rise there, and then it drops back a little, and it's not till the 60s that the exponential takes off. Now, what did it in the 1940s? I don't know, but before I give the next talk, I'll look into that, and I'll try to have an answer for it. Okay, yep.
The necessity for water. Are there other liquids that life could grow in?
Okay, the water is first of all ubiquitous, and it's a very convenient molecule for dissolving other substances. And the only thing people suggest that could maybe replace water, I've read, is silicon. But it's not as desirable, so it's not, our DNA and so on, it all depends on water. I mean, you know, our bodies are 80% water, right? So,
But for other
yeah, you know, I can't rule it out because I just don't know. But people have investigated silicon in particular. It's on the periodic table somewhere here. It's you know, next to, it's in the same column and has some of the properties of water, but it doesn't combine as readily with as many substances. It seems like water is uniquely suited to producing the complex the molecules that we need for life.
and it's commonly available in other.
It's everywhere. When I was a little kid, I read a book on cosmology that was written much earlier, probably early part of the 20th century. And they said, well, Earth may be the only place in the universe with water. Now we know it's everywhere. It's throughout the galaxy. There's huge clouds of water. There's water on Mars. There's water on Enceladus and Titan. Enceladus around, is that Jupiter or Saturn? One of them. And what's the other one? Here you go. Here's your.
We will bring Mark back to give another long talk so that you can question him and grill him as much as you want to later. All right? And you'll also probably be able to find him wandering the halls, particularly when you're up near Pan Stars, so you can ask him questions there. All right. Yeah. All right. All yours. Thank you.
Yeah, that was Dr. Mark Willman. One of the comments that Mark made that might be better clarified is CFC is refrigerant, and refrigerant was banned. So when you replace an air conditioner generally, you've got an entirely different refrigerant than the one that was making a hole in the atmosphere. The other comment that Mark Willman made was regarding DuckDuckGo, spelled D-U-C-K-D-U-C-K-G-O. That is a browser. It is nowhere near as good as Google Chrome and some of the others, but you are completely browsing privately. So something to take a look at. But I was corrected, and that is correct. That is a search engine. Thank you. I'd like to introduce the next speaker. I consider Dr. Tom Chad a celebrity. He is an awesome man, and his subject is, as you can read, the Citizen Kate experiment. We're all going to learn what that means. Kate is Continental America Telescope Eclipse, which I'm sure he will tell us what that exactly means. Dr. Shad's background includes being born and raised in North Texas. Born and raised. Sounds like a bumper sticker. Studied physics and philosophy at the University of Notre Dame. There's so many ways to pronounce Notre Dame. Trust me. Graduating in 2007. In 2013, completed his PhD at the University of Arizona after developed techniques to study the magnetic field of the chromosphere of the sun. Dr. Shad moved to Hawaii to work on the development of one of the UH instruments for DKIST. Now you're probably hearing DKIST repeatedly here. That's the Daniel K. Inouye Solar Telescope, for those that are not into acronyms, and now works for the National Solar Observatory as an astronomer with the DKIST project. Dr. Shad will help us learn about the Citizen Kate experiment. With that, please give your full attention to Tom and help me welcome Tom Shad.
Great. Welcome, everyone. Thanks for coming out tonight and enjoying our 50th anniversary here at the IfA. I get the pleasure to talk about something that's very, very exciting that's happening 44 days from now. Who, and I have to ask in this room, maybe raise your hand, did you know that there was a solar eclipse happening in 44 days? Okay, almost the entire room. Anybody traveling for it? Couple, 3, 4. Well, 5. Something that hasn't happened in the young history of the United States as a country is about to happen, and it's very, very exciting. And I, as a scientist with the National Solar Observatory, have been blessed to be a part of this experiment called Citizen Kate, which Citizen Kate is being led by an astronomer out of Tucson, also from the National Solar Observatory, but encompasses and consists of amateurs and students and institutions and national parks across the whole country with the one goal of making the very first mega science quality movie of the solar eclipse. We're going to make a 90-minute movie of a solar eclipse using 68 telescopes spaced 40 miles apart on the continent. That's incredible. It's really an incredible feat, and there's a lot that goes into it. But tonight let's start a little basic just to get everybody on board here. Solar eclipse, very briefly, very simply, it occurs when the moon and the sun and the earth get into an alignment. In particular, whenever the moon is between the sun and earth, we have solar eclipses. When the moon is between the earth, or the earth is between the moon and the sun, then we have lunar eclipses. Basically, the shadow of the earth is cast upon the moon in lunar eclipses, but during a solar eclipse, the shadow of the moon is cast upon us. So eclipses occur when this happens, when this alignment happens. And it just fortuitously happens that the moon is about 400 times smaller than the sun, but is also 400 times closer than the sun. Just randomly, right? Just amazingly. And what this happens is whenever you combine the orbital motions of the Sun-Earth-Moon system together with these close distances, you have a variety of eclipses. You have three main types of eclipses. The first one we experienced here on March 9th, just last spring, in 2016. It's a partial eclipse. This one's about 50% or 60% totality. This one was measured in Minnesota in 2004. When the moon is a little closer to Earth, such that whenever it passes in front of the sun without covering the whole thing, we have an eclipse called an annular eclipse. So in this image, we have the moon here with just the ring of the sun on the side. And if you've ever experienced one of these, it's really kind of demonic in the sense that as the moon comes in, you see these devil horns of the moon coming into view. But then when very, very special conditions happen, we have a total eclipse. And these are very, very special phenomenon. And in particular, we have to say what makes a total solar eclipse so special. This is an image now, I forget where it's taken from now, of a total eclipse off on the horizon, and you can see the glow of the sky on each corner, and you can see stars as well. During a total solar eclipse, we get to see the sun at night, basically. It means that the sky brightness has dropped. And basically anything that's dim that would otherwise be completely saturated by the brightness of our sky, we get to see. So we get to see the sun at night. We get to see these dim objects at night. And for us, what's really amazing about the sun is that we get to see the sun unlike anybody would ever have seen it before. And to be a prehistoric person on this planet, to see a total solar eclipse, you must be absolutely just mind-boggled by the next picture. Whenever the moon crosses across the sun and you get to see the brightness of the solar corona that extends outside of the sun, you get to see actually the true nature of the magnetic sun. What we're seeing is an eclipse. Forgive me, I actually forget where this one's from. I think this was 06. This was taken by Shadi Hadal at the University of Hawaii. What we get, though, is the corona and the chromosphere revealed. So near the limb of the moon, or the edge of the moon, and on the edge of the sun, we get to see these little red objects. These objects are called prominences. They're big clouds that extend above the surface of the sun in a region that we call the chromosphere. Out further, we get to see the hairy magnetic beast that is the sun. Each one of these corresponds to a magnetic structure that completely surrounds the sun and actually is blown out into space. So what you're seeing is the magnetic field of the sun, but also the extension of that magnetic field where the constant or quasi-continuous magnetic solar wind of the sun is blowing this magnetic field out into interplanetary space. And in fact, our Earth system and all planetary systems in our solar system are completely enveloped by this magnetic field. The magnetic field of the sun is really what we define as the edge of the solar system in many ways. If you consider where the end of the magnetic field of the sun ends, it's 80 to 100 AU, which is 80 to 100 times the distance between the sun and the Earth. For reference, Pluto is at 29 AU. So some 2 to 3 times further away than Pluto is where the sun stops. So we live in the sun. And when you know, we've seen views of the corona now for centuries. There's drawings and photos of the corona from the 18th century, drawings well back many centuries ago. But now we have this whole modern industry of solar physics that I'm a part of, and that DKIS, the Solar Telescope, is a part of, because we now know that when this magnetic field interacts with our local plasma environment of the Earth, and when you couple in the fact that there's dynamics of the sun and storms and energetic particles, it becomes a very important problem to understand for our modern electronic Earth. Basically, any big solar storm that's coming off the sun gets pushed out into space in some way, gets accelerated, and then gets thrown out in a particular direction, and sometimes it can come out towards Earth. So to understand the corona is to understand these processes that influence storms as they go out. So a fundamental question is exactly how the magnetic field of the solar corona is structured and how that lends to this storm propagation. So eclipses are very special, but they do happen quite frequently. So we can ask ourselves how frequently. Well, between 2 and 5 solar eclipses happen every year. Total solar eclipses are a little bit more rare, but they also occur approximately every 18 months. So why am I making a big deal about the USA one? Well, let's get there. Well, once you start thinking about the chances of seeing a solar eclipse in one particular place, the statistics go a lot more against your favor. So statistically, total solar eclipses visible from the same spot on Earth twice. Statistically, it's about every 400 years. Some places it's much longer than that. You might have to wait 2,000 years, 3,000 years before you'd ever see a total solar eclipse. There will be entire generations and entire civilizations that will maybe have gone without ever seeing an eclipse because of that fact. In Hawaii, we got to see one in 99 or 91 off the Big Island, but the next one in Honolulu is 2252. So
And it was cloudy.
it was, yeah.
On a boat in the channel and not seeing it.
So the only eclipse I experienced on Hawaii was last March, and it was also cloudy. And if you look at the rainfall of last spring, Kihei was completely dry up until 1 hour before the eclipse, and then all of a sudden. Yes, we will. Sorry, I'm going against that, but let's get to that. That's my last slide, actually. So this is what the total solar eclipse path on the mainland looks like. And what this shows is there's a lot going on in this plot, but basically the yellow line here is where the totality is. You have to be along this path in order to see the total solar eclipse. Anywhere else, it's a partial solar eclipse. That path is about 60 miles wide, and we expect tens of millions of people to flock to it here in about 44 days. So there's a huge effort going on by these 12 states. This is 12 states across this to facilitate the tourism that's going on with this event. For example, I'm going to a town of 2,000 people in Central Oregon that's expecting 60,000 people on the day of the eclipse. John Day, Oregon. Oh, sorry. The question was which town I'm going to in Oregon, and it's John Day. That was right. So there's other things on here as well. You can see that, indeed, in Hawaii, we do get to see about a 30% of an eclipse. But this edge of this map says eclipse ends at sunrise. So we're going to see an eclipse, but it's only going to be about for an hour after sunrise. So you're going to have to be in a very special location and get lucky with the clouds to see it. Meanwhile, on this side, it's basically where, if you're viewing an eclipse in this location, it will be at sunset. But it's not 12 hours between these two locations in terms of the eclipse path. Instead, this is where the eclipses are in terms of Greenwich Mean Time. So it's 1715 to 1845. So 90 minutes there. This whole thing is, I forget now how long it is. But here we go. If you measure the speed, the average speed of the moon's shadow is 1,700 miles per hour across this path. So if you were, say, to try to fly in the totality path so that you see the total eclipse for longer, you need to be going Mach 2.25. which is indeed exactly what we tried to do in 1973, or at least some scientists before me did with the Concorde jet over the Sahara. They were trying to do exactly that. The longest duration of this particular eclipse, they vary. Eclipses can be on orders of 1 to up to about 7.5 minutes maximum. This one, the maximum is going to be 2 minutes and 40 seconds in a place called Carbondale, Illinois. It depends on the orbital motions, in particular how far the moon is from the sun and exactly how much it's over. The moon is oversized compared to the sun, right? If the moon is closer, then you have less time where the moon is covering it. Yeah, that's part of it. Now, why is it special? One of the many reasons that it's special is here I said, since the birth of our country, we haven't had one that's completely across the United States. So this is all the eclipses from 1776 till now. And this is the eclipse path on next month. So you can see it's just beautifully banded right across the country. If you think about what eclipses are coming up, it's special, but there's actually one more coming up fairly soon in terms of astronomical timescales that we're also interested in. Here's the next opportunities. First, August 21st, here across these 12 states, coming up in 44 days. The next one, April 8th, 2024, 7 years. This one. This is going to be the next exciting story. But then after that, 33, Alaska gets to see it, and then 44 and 45 are the next kind of opportunities, and they're very brief. So imagine just how many people live along this path. It's some 10 million homes. Everyone's within, well, 200 million people are within a day's drive of the eclipse path. So it's special just from a phenomenological perspective. But why is it important scientifically and personally now? So it's beautiful to look at for sure. So here's the eclipse image, and below you're going to be seeing a movie of modern EUV spacecraft images of the corona, showing a lot of dynamics and a lot of things that we modernly study with spacecraft around the Earth. But if we think about the importances here, one, it is visible from everywhere in the U.S., Hawaii, Alaska included. 320 million, approximately, will be able to see some sort of an eclipse. And millions, tens of millions will travel to the eclipse totality path. This is 2,500 miles of an eclipse across the land. If you go back to one of these maps here, let's see. I have to go to this one. You can see any blue line here is a total eclipse. For example, this is a total eclipse. But you'd have to be on a boat or in Chile to see it. Similarly here. It's very special in order to be able to have access to a total eclipse across land for so long. Even eclipses that go across southern Africa or northern Africa, access in those regions is very difficult. U.S., you have a modern infrastructure across 2,500 miles in order to study and experience the eclipse. So it's incredible access for public viewing and also science instruments. There's real science actually as well. Even though there are all of these modern images and modern images of the corona, you can see that most of these images are showing you close to the sun. And that's the fact of the brightness of the EUV corona is kind of limited to very close into the sun. You don't get to see this piece of the sun from these spacecraft. Only during an eclipse do you get to see this area. And this is where that magnetic structure and the dynamics are kind of actually really important for the acceleration of storms as they go out. It's also a test bed for new techniques. Many of the techniques that we've developed over the last 3 decades that are going to be going into the instruments that are built in the lab down the hall and it will be up on the summit in 3 years operating for scientists across the country and world started with an eclipse. Jeff Kuhn and others went to eclipses and measured spectral lines in order to do that fundamental science. But for us, citizen science and the training of a generation of scientists, what an opportunity we have here in order to enhance training of science. So to put a highlight on exactly that region that we're studying that's different than space, here's another spacecraft image of a storm in outer space by an instrument that creates a fake eclipse. So this is actually a little metal disc here that covers up the sun. The sun is right there. And what you can see is a huge storm that's coming off, right? This, remember that there's 110 Earths across the sun. So imagine how big this storm is. Well, here's the sun. Here's another instrument in space. And this black region is actually the gap that we never ever get to see except for during eclipses. So if we blow up that, what we're interested in is understanding this critical link between the low corona and where this expansion happens. So that's the driving science, or one of the areas of driving science for us in terms of studying eclipse. The experiment that's going to do it for us in 44 days is called Citizen Kate. And I've already introduced it a little bit. Basically, our goal is to empower citizen scientists, amateurs, students, universities to make a 90-minute science quality movie. So it travels from Oregon to South Carolina over 90 minutes. The totality lasts 2 to 2 minutes and 40 seconds at any given place. Citizen Kate deploys 68 identical telescopes, which is very important here. There are other projects that are going to try to make a mega movie with iPhones, for example. That's going to be great, but this is a whole different science level in the sense that we're using science-grade equipment. We're going to place them about 40 miles across, apart. We precisely coordinate them and synchronize them with GPS antenna. And then at each site, we take about 1,000 images in that 2 minutes, so that at the end, assuming everybody gets clear weather, which some have been assured that they will, we end up with the movie of about 70,000 images of the sun over 40 minutes. And this work is supported by a number of institutions. Yep.
Why do we care about what happened? What is the reason that you're studying this?
I can give you the highlights at the end, but sorry, the question was why are we, what are the main science drivers, if I correct me if I'm wrong, the main science drivers for studying this? I can point you to the website or we can talk afterwards, but one thing in particular is polar plumes. There are plumes on the poles of the sun that are very dynamic that we don't have a great understanding. Another one is oscillations. We often see wave activity in the corona that is related to the acceleration of storms. These are in part some of the things that we're interested in. So this is the deployment map of all the sites. So the different symbols here correspond to different types of sites. So the yellow ones are private sites, basically amateur astronomers who have funded their own equipment. The red ones are universities, the blue ones are high schools, and the green ones are associated with parks, state and national. This blue one here is John Day, Oregon, where I'll be in a couple weeks. Right, so it's one of the sites that's on this eclipse path. So it's one of the 68 sites that are spaced apart. And why I picked that site in particular, one, it's close to Hawaii. Two, it's one of the second best weather site on the path. So I got lucky, but other people have to go other places. So here's John Day, where I'll be. The eclipse is going to be 2 minutes and 9 seconds at that spot. So the equipment actually was just shipped to Oregon 2 weeks ago, but it was actually outside here about 3 weeks ago. We were doing testing. This is what the telescope looks like. So it's a 80 millimeter f6.25 apomat refracting telescope. So there's a lens up here that forms a focus down in this area. For the times of the observations that are not where the sun is not completely covered in the moon, we have to use a filter. So this is a solar filter on top. We take that off whenever the eclipse is happening. We have a pretty sturdy equatorial mount to protect us from wind. Then we have a 5 megapixel camera here that operates at about 8 frames or 10 frames a second nominally for this observation. So 5 megapixels, so that's 2,500 pixels on a side basically of an image. We control it actually by a little box here which has an Arduino electronic processor there that feeds in a GPS signal. So we actually use a GPS signal to help trigger the camera to a particular time. And then the data is read actually out of this USB camera into a control computer. There's a lot of steps to the observing procedure that in order to coordinate a team of 60, that consists of 68 teams, which means on order of 500 to 600 people, this has been a huge feat of organization. And there's an established procedure for everybody, but what we've also been doing is we've been running a lot of workshops. And I can't take credit for any of this. Actually, this has all been Matt Penn out of Tucson and his team of undergraduates that have been with him for about 2 years working on this. This is one guy out of Wyoming who's been working on the project for quite a while now. These are just some shots of various workshops. We've had workshops in every single state. We had a state coordinator in each of the 12 states. We had workshops, 2 to 3 workshops in every state in order to train everybody on the equipment. Some people were senior pro. Some people were very new to the instruments. The team I'm working with, for example, doesn't usually take observations with these types of telescopes. So there's a big learning distribution. But even senior pros, we have to learn ourselves. So the workshops were early so that we got the procedure out to test it. We practice, and we learn some things. We learn how to do it more efficiently, how to do it correctly. And in some cases, we learn that Tucson, Arizona is a hot place to live. So literally a piece of the equipment that never made it to Maui was this fan. This fan was a very specially target selected fan that is now being used in order to make sure that the camera and the computer do not overheat in the sun, because the camera will stop working if it's in the sun too long. So this is a very technically special fan that literally blows across the camera. So some sample images, just a few. This one is actually a lunar image that we were practicing with 4 weeks ago, just outside. So this was taken just outside here. This one was taken in Wyoming, I think, that shows the full field of view of how big the field is going to be. This is another practice shot. Here's actually a shot of somebody who magnified the image slightly, showing the sunspots that are on the sun right now. So this was this morning. So from here, where do we go? Well, Kate is gearing up. We're all excited. The next 44 days, there's individual practices, but there's also coordinated practices. We're actually coordinated. We're doing practice runs as a full team. So each site is taking observations on the same day or two, and then we have to report back all the data. And on the day of the eclipse, the idea is actually to give an image over to Tucson so that at the end of the day, we have a first look of the eclipse movie before all of the science data gets fully processed. So there's a lot of work, a lot of practice to be done in the next 44 days. I'm going to be in John Day about 3 days in advance to make sure everything is working properly and that we're up to snuff and the site looks good. But then August 21st comes and we turn this image into a movie, which has never been done for an eclipse before. This is an eclipse image, but we never had a movie of it. We don't know what dynamics are really there. I mean, we have some idea, but we've never seen it. But then what's important here, and actually what's really unique about this particular citizen science campaign, is that while we get all the data and we go in and study our particular science goals, which include polar plumes and magnetic structure and oscillations, et cetera, the schools and the groups that were funded by a nationally funded grant keep all of their equipment. So the school all the equipment that we had out here, going to the school on John Day, and they keep all of it, and then they use it for all of their astronomy club and science activities of their school. Schools that are local, small schools in most of the cases in these paths, who would normally not have equipment of this grade, all of a sudden get launched into a science grade telescope. So it's really quite, yeah, it's great. So just wrapping up, last 2 slides here. What will we see in Hawaii? I already showed you this a little bit. 6:06 a.m. is the sunrise on August 21st. If you're lucky enough to find a spot without clouds, and you'll see a little slight glimmer of the eclipse in action. It's right before the maximum, actually. The maximum happens about 20 minutes later. 30% coverage, 6:35, and it ends at 6:22. And 722. And here I just put in a picture of Haleakala sunrise, and I checked last night. There's still 61 spots of reservations left on the national park. So if you, it's a Monday morning. I didn't say that, but yeah, you probably could. Yeah, you probably should if you want. I won't promise anything. My track record for Hawaii eclipses is terrible. But if you're so lucky that the clouds are low enough and you get there on a nice morning, it could be pretty nice. And you can see it. You'll be able to see it just with your eyes, but you do need solar viewers to protect yourself, protect your eyes. If you need some, we have some. There's some outside. I have a whole box of them upstairs. Just ask me. And otherwise, thank you all for coming tonight. And there's a whole special eclipse site, one of many across the U.S. for this eclipse. But the National Solar Observatory has one at eclipse2017.nso.edu. And it tells you all about the science and all about the equipment in much, much, much better detail than I've given tonight. And a lot of your questions can be answered there. Otherwise, thank you. The question was, how would the movie be distributed? You mean to the public? I don't know for sure exactly how fast it's going to be turned over. The goal is to have a movie ready day of, which I'm sure will be put in the press within 48 hours. And then all of the data, I don't know what the data policy is going to be, but probably at least the first 6 to 12 months will be just the scientists who are a part of it who will be using the data. Yeah.
Will they show the film here?
We will definitely have it here. So there will be an upcoming talk that will show it. Yep. Question?
Is all that gloomy stuff visible with the naked eye? If you're there?
Not at that fine structure, but the global structure with the big plumes is there. Yeah.
That picture.
You'll see. If I go back, you won't see the fine hair so much, but you will see these streamers. You'll see these plumes like this, these shapes, but the very fine stuff you won't see. Bare eye. Yeah. Any other questions?
So you implied that viewing the corona of the sun using the solar eclipse, or the moon, does it offer more to us than maybe just using an artificial eclipse? You know what I'm talking about?
Absolutely, it does. Yep.
Did you go over that? I don't remember.
I didn't go into it in great detail. So when the moon goes in front of the sun, what we basically see is about 1 million times worth of light gets knocked out. So this corona, for example, is 1 million times fainter than the disk of the sun. So we need the sky basically to be dark to see it in this detail. We can create artificial eclipses, and we'll do this up on Haleakala, but those only knock down the light by 100,000 or so. So it's still much harder to measure the sun that way than to do it at the eclipse. There's nothing on Earth that creates an eclipse this nice artificially. Yeah. Yeah.
Is that right? It's safe to look at a total eclipse while it's total?
Yes. Yeah. So, again, so it's 1 million times of the light. The question was it safe to watch a total eclipse when it's in the totality phase? And the question is, and the answer is yes. 1 million times, or 1 million's worth of the light has been filtered out by the moon, which is actually more light than filtered out in the solar eclipse glasses, for example. Yeah. So it is safe. And in fact, you should. If you're in the totality phase, you definitely have to take off the eclipses to see the eclipse glasses to see this. Yeah. Anything else?
Well, for those people who would like to attend the monthly meetings, if you're not on the mailing list, the emailing list that is, please give your email address to the lady at the front desk, and you'll receive the email that announces the monthly meetings and talks that are held here. not an obligation. You're just going to receive an email, and you can come or ignore it. But we're really grateful for your attending tonight and attending the annual and also the 50th anniversary open house. And thank you, Dr. Tom Shad.
All right, thanks, Mark.
Mr. Awesome. Thank you.
Thanks.